Good afternoon. So we have now reached the end of our course, and this will be our final lecture. Now, right from the beginning, we had three goals which we have achieved to some extent. The first one was our understanding of how the microscopic random motion of particles, because we are looking at transport, can be related to continuum descriptions like of the concentration field. In the simplest case, we have a dilute solution of some Brownian particles. They would satisfy, their concentration would satisfy the advection diffusion equation with Fickian diffusion, right? And the individual trajectories would satisfy usual Brownian motion equations, right, or random walk equations. And this microscopic description one will encounter in basic books, either on stochastic processes or on Brownian motion, right? Especially if you're looking at topics in biology, the random walk is something that will be introduced early. Now, on the other hand, in any course that involves continuum mass transport processes, you will start with the Fickian diffusion. And these two things are really the same, but how do we relate the two to each other in a rigorous systematic way? Because if you can do this, then you can, of course, relate the same for more complex systems which don't do just simple Brownian walk. Right? So that was the first point, and that's what we addressed by starting with stochastic processes in general and seeing that if they are Markov and continuous, you can write down a Fokker-Planck equation, and this takes the form of a diffusion equation generalized in the probability space, which coincides with the concentration diffusion equation if you have constant space diffusivity and dilute system. Okay? But that generalizes the idea that if I have some stochastic random motion happening for an individual particle or agent, right, or system, then I can write a continuum description in the probability space where I will have a PD. Okay, where you have drift and diffusion terms. Then we went to the individual trajectory model and saw that we would naively model it as a Langevin type equation, which basically says I know the deterministic physics governing the problem. So let's say I have a particle, it's moving in the flow, for example, right? Or it's an object, a bacteria that is swimming, so you know its swimming velocity. So whatever the object or system may be, you have some physical input to write down deterministic ODEs for it. Right? And now you want to add noise on top of it to model what you don't know, typically. Right? So it could be turbulent transport that you want to model away, right, by putting in it as noise, or it could be the thermal fluctuations which you are not modeling. Right? So either way, you add in a stochastic term to represent that stuff. And this takes the form, if you just add on white noise to the ODE, it will be a Langevin type equation, but we know mathematically this is not well posed because the white noise limit, if you just write it down as a forcing term, will have infinite variance, etc. So to regularize it, we had to introduce the concept of an SD, and the main point there was to realize that if I look at the integral of such an equation, right, as the solution, like what are the solution trajectories, there would be an integral, right, and that integral would be what's called a stochastic integral, where the answer will depend on where you evaluate the integrand when you do a Riemann sum. So then we said, okay, we have to resolve this in some way, and we started with the Ito definition, right? And then with the Ito definition, things become simple in ways we could derive the Ito's formula. And finally, you were able to show that, okay, this SDE makes proper mathematical sense and can be connected to a Fokker-Planck equation, which connects the first two parts of the discussion and answers the first part of the course. Right? But then we had to see, okay, fine, this Ito definition is fine, but what would actually correspond to my physical system, which I typically am looking about something that is being forced randomly, but with finite correlation in time. And then I want to take the correlation time going to 0 just as a simplification, as a simplified limit, looking at the extreme case of infinite difference in time scales between what I am observing, which is the slow dynamics, and what I am modeling away as noise, which is the fast dynamics. And that limit becomes Stratonovich in 1D, and some, not exactly Stratonovich, some correction to Stratonovich in multi-dimensions in general, right, for non-equilibrium processes. And we were able to derive this using what's called, in the stochastic processes literature, it would be called adiabatic elimination. But we showed that it's basically, we saw that it's basically the center manifold reduction, right, but applied to the Fokker-Planck equation of the corresponding set of ODEs and SDEs, right? And ultimately, you can get only SDEs where you have removed out all the fast variables, right? And then you model them as white noise. So we saw nicely how we could connect this derivation to center manifold reduction that would be used, for example, in problems like Taylor-Harris dispersion. Applying that to our system, we were able to derive the weak result that indeed in the limit of white noise you get Stratonovich for 1D or for reversible processes where the noise autocorrelation tensor is symmetric, right, in multi-dimensions. If it's not symmetric, it's not exactly Stratonovich, but we know how to derive the corresponding SD. So this fully connects our first part of the course and second part of the first question and second question. Second question was, of course, how do we understand SDs, Langevin equations properly, and the white noise limit. So all of this has been done. And then the third point was how to use all of this to model turbulence. One specific intriguing point we raised was if you think of a flow and you model a wave as a random field, and now you ask how does this random field mix, for example, a spot of dye. And we saw if you just naively take the average of a advection diffusion equation where the velocity is random, and you assume this random velocity is uncorrelated with the instantaneous concentration distribution, then you get no mixing. There was obviously a problem. Now when we looked at it again with all our tools, we could realize that, oh, it's a Stratonovich limit because it's random velocity field multiplied with velocity gradient, right? So the random stuff, which is the velocity field, is pre-multiplied by velocity gradient, which of course depends on the field. So it was a multiplicative noise. We take the Stratonovich limit, which we can justify because we showed the autocorrelation tensor of that homogeneous isotropic Kraichnen model for the turbulence is symmetric, right? The correlation matrix will be symmetric. And that's what we did in the previous class. We were able to then derive exactly, if you take the averaging, take the Stratonovich interpretation, convert it to Ito, average out, and you find an extra drift term that is nothing but mathematically exact eddy diffusion. So this, you're able to show that this random Kraichnen homogeneous isotropic field gives rise to eddy diffusion in the mean. Okay, so this was really the high point of our course where we could now use all the machinery we had learned to prove this nice result. Okay, so now what I want to do today is just introduce some resources, okay, for the last lecture as well as for other applications of what we've learned. So firstly, regarding the Kraichnen model, which I taught last time. So what we did in the last class is kind of the most basic result one can get using the Kraichnen model. It uses only the variance of the random field comes into the eddy diffusivity. Now with the model one can study much more details about this scalar field that is being transported, in particular the structure factors and so on, which are used to reveal intermittency. And it turns out that if a scalar field is transported in real turbulence, it's intermittent. Right? And in physical space you will see that the scalar field has ramp cliff structures. That means there are very sharp gradients in the concentration field. And this leads to very larger than expected high moments of differences in the concentration field. So they're called the high order structure factors. So these are things that people have seen in DNS and so on. Right? And this gets reproduced by the Kraichnen model. That's why Kraichnen model is particularly interesting to understand the source of this intermittency. And with the Kraichnen model, one can analytically show how this intermittency arises through what are called zero modes and so on. These things we will not cover in this course for lack of time, right? But it's one direction in which, with the basic stuff we have learned here, you can push your study further. So all of this and more is discussed in this book, rather in the following chapter. So it's a chapter written by Gavetsky called Soluble Models of Turbulent Transport. Right, it is chapter 2 in the book. Non-equilibrium statistical mechanics of turbulence. the London Mathematical Society lecture notes. Okay, so this is a chapter quite dense with a lot of information, right? But very rich, in which you can first of all find the initial developments that we did in the last class, right? And the result that the Crichton model gives rise to a diffusivity, which scales like the variance of the velocity field. But much beyond that, into the structure factors of the scalar field. And then also discussed there is how, if you put a line element in the Crichton flow, how will it stretch? Right? So the stretching of line elements, of course, is given not by the velocity, but by velocity differences at small scales. In other words, by the velocity gradient. So just like with the Crichton model, you have a velocity field. One can of course take the gradient of that because it's a smooth field, even though it's fluctuating in time, right? One can look at the velocity gradient, which is also random because it's coming from the Crichton model. So one can have a Crichton model for the velocity gradient, and the velocity gradient is a tensor. So all the same things we did in the course so far can be applied even to the velocity gradient, except that the noise is now tensorial instead of being a vector. But the same results that we had for Ito's formula, etc., can be generalized to tensorial noise. And therefore, you can then study stretching of line elements in a turbulent flow, again by modeling the turbulence. Again, this is something that we will not have time to cover in the course, but is a direction in which you can naturally proceed. Now, why would a person be interested in studying line element stretching? Well, it tells you something about the chaos, Lagrangian chaos of the flow, meaning if I have two tracers close to each other, how would they separate? Would they separate? Right? And if the flow is chaotic, they will eventually separate out and separate out exponentially, right, on average. And this is all these properties you can derive for the Crichton model. But in terms of applications, it also has applications to understand how particles and stretchable objects behave in turbulence. So you have tiny objects below the Kolmogorov scale. Because the flow is chaotic, their ends will tend to stretch apart, right? And if they are stretchable, they will stretch, right? But of course, they have some elasticity which tries to keep them from stretching forever. So you reach some sort of dynamic balance, and you'll get a distribution of states of the object with different extensions. Okay, a classic example of this with many applications is polymers in turbulence. And there are many reasons to look at polymers. One well-known reason is that if you have turbulent flow in a pipe and you add even a few ppm of polymer, you can dramatically reduce the drag. Right? So you can save energy costs in pumping, for example, oil. Even firefighters who shoot water out of a hose, if the water contains some polymer, it carries to much greater distances because the drag is less, right? It loses less energy in dissipation and more kinetic energy survives. So there are many applications, but the point again is that polymers are tiny objects which can stretch, right? So if you want to understand how much or how do polymers behave in turbulence, how much do they stretch, etc., you can model it by replacing the turbulence with the Crichton model. So as a way to explore these, this application, okay, of polymers in turbulence, there are some things you can look at. So there is a YouTube talk or lecture, right, by me. Okay, so there's a YouTube talk which I have given entitled Stretch Coil Break, the Turbulent Voyage of a Polymer. It's on the ICTS YouTube channel. It was part of a workshop in soft matter. So that gives you a kind of overall introduction to this topic, and a couple of assignments, final projects in this course are based on this. In addition, there are many papers, right, So I will just give a couple of them, which will be useful. Okay, so there is this paper by Plan, Ali and Vicenzi, 2016 in PRE, which shows how you can generally use the Crichton model to study the deformation of a hierarchy of different kinds of objects, which can be modeled by bead rod kind of models. So that can include polymers, but also more complicated stretchable objects. Okay? And there are many papers before this, in particular by the group of Vicenzi, which have studied this problem in great detail. Okay? So how the main point that I addressed here is how, in terms of the velocity gradient, the fact that it's a tensorial noise, how you can deal with it, again using the steps that are in Gardner's book. Okay? So some useful steps are outlined in this paper. And then for a more specific case of polymers with an overview of the literature, you can look at this paper in JFM, which again looks at polymers and different aspects using the same model, but compares it also to direct numerical simulations in turbulence, and shows that the Crichton model works quite well even to predict the stretching of polymers. Now these topics are quite, they're specific areas, right? So it's something that you can decide to pursue depending on what kinds of problems are of interest. Okay, so coming back again, if you want to understand fundamentals of turbulence theory like intermittency and how does it arise, particularly when it comes to turbulent transport of fields, then it's good to look at Kavetsky's chapter, right? And then there are several other review articles, but these are cited here. And at least that's a starting point. Then if you want to look at objects in turbulence, right, and Lagrangian transport, then a prototypical example to see the power of stochastic modeling would be polymers, right? And then you can look at these resources. Now, the last thing I want to talk about is something more picturesque, okay, which is using turbulence as a way to understand the emergence of large-scale patterns. Okay. So a classic example, which you may have already noticed, is that of cloud streets. So what are cloud streets? I'm sure you would have at some point looked up at the sky and seen the clouds arrayed in nice patterns. So of course, each individual cloud, particularly in India, right, where we have tropical climate and you have strong convection in the atmosphere, the clouds take the form of what are called cumulus or cumulonimbus clouds. Right? So they are big, cottony ball-like towers of clouds, right? Not these wispy kind of things. Right? They are very big, right? Like cauliflowers. Right? So now, and they can form very big towers and fascinating shapes, but that's all an individual cloud. Okay? That's also very interesting, but not what I'm talking about. What I'm talking about rather is when you look across the sky, you see that, okay, there are patches of clouds, but they're not random. They seem to be organized in some fashion. So one very clear organization is when they arrange themselves into streets. So it will look like this. Okay, so there's a cloud, then no cloud, then there's cloud, then there's no cloud, then there's cloud, and so on. Okay, so they are like lines of clouds. Okay, and this spans many kilometers. And typically this happens if you have an icy landmass. So you will not see this much in India, okay, but at least this thing. But you see it off coastlines, like more towards an Arctic. Right? So if you have an ice landlocked mass, right? So this is cold. Then the water or the sea is relatively warm, right? And the ice is cold. And so when you have wind blowing over the ice, right, from sea to land, then you will get cold air, which has been cooled over the land, suddenly coming over water, and more or less uniformly, right? So you can imagine you have this uniform wind blowing, and so you have warm air now sitting on top of, cold air sitting on top of a warm water. Okay, so this sort of situation looks like the classic Rayleigh-Bénard problem, right? You have a cold plate on top of a hot plate. Okay, so this would be a kind of ultra idealization of what's happened here. Right? So what happens now if you have hot fluid down and cold fluid on top is it's naturally unstable, right? Because hotter fluid is less dense. So you have more dense on top of less dense. And if you give a small perturbation, right, the hot stuff will tend to rise up and the cold stuff will tend to come down. So this is, if you start out perfectly uniform, of course, all the forces are in balance, right? It's like having a top standing on a table. In principle, it should remain there if it's perfectly aligned, right? But of course, the smallest perturbation, forces are misaligned and it will fall or it will rotate or it will do something. So same thing here, the smallest perturbation, which of course is there, right, all the time randomly, will trigger motion. The system becomes unstable and it transitions to a new state. So this is the classic problem of the Rayleigh-Bénard instability. And that gives rise to cellular rolls. Okay, so you will get cellular rolls. Now this problem is of interest in the theory of pattern formation because you start with a featureless state with hot fluid down, cold fluid on top, and spontaneously you will trigger convection patterns. So the way to do it in the laboratory is you start where maybe both balls are at the same temperature. So then everything will be dead and motionless. Then slowly you increase the temperature of the bottom plate, and at some critical point, the fluid will spontaneously start to convect. And what's interesting is when it convects, it will not do so randomly. It gives rise to a nice array of rolls. And if you look at it out of the plane, if you look at it in 2D, you will see these things aligning like this. Okay? So they are called convection rolls. And if you just look at that situation is very similar to this. Okay, so one would, if you just look at it naively, you will say, oh, these are similar to Rayleigh-Bénard type rolls. Of course, granted that there are various kinds of inhomogeneities in the realistic problem, right? And then you also have effects of radiation, how the cloud feeds back thermally. So when clouds form, of course, water condenses, that releases heat, so on. So there are, of course, many things going on here, right? In terms of water vapor being present, radiation, and so on. But at first order, you would say, oh, this is a Rayleigh-Bénard type of convection roll phenomenon. But the biggest difference between these two, right? So this is usually done, remember what I said, it's done where you have a completely still fluid and then you bring the bottom temperature higher till you just start convecting. At the onset, you get these nice rolls. Now, if I keep on increasing the bottom plate temperature, or if I increase the height, or I make the fluid less viscous, right, it basically means I go further and further from the onset of convection, this starts becoming turbulent. And then you will destroy these patterns, at least initially. So the biggest difference between seeing patterns here and patterns here is that this is just at the onset of convection when the flow is laminar. Okay, so here it is laminar, right, just at the onset. The fluid was completely still and it just started to convect, so it is completely laminar. Then in some sense it's not surprising that, okay, you are seeing, it's still surprising and interesting from pattern formation perspective that these rolls are organized and why they are aligned in the way they are, etc., etc. But the flow is laminar. Right? On the other hand, here the flow is strongly turbulent. There's no question of being laminar. Right? And when the air comes over the water, you are not controlling the temperature and slowly increasing it. It's a sudden thing where you have cold directly over something much hotter. So you are very far from the onset. And you should expect turbulent convection, and in fact, it is turbulent. Right? So this situation is turbulent and far from onset, whereas this is laminar. Right? So that, if you like, is the biggest difference between these two, I would say. And it's that's what makes it very surprising, that even in this case where the convection is strongly turbulent, and in fact, if you zoom in into any one of these clouds, the flow is at extremely large Reynolds number, right? Completely turbulent. So when you zoom in, you're fully turbulent, but why when you zoom out, you see order? Right? So how is it, in other words, that despite the turbulence at all scales, you still have this very nice pattern emerging, which is somehow reminiscent of what happens just at the onset of convection when the flow is completely laminar. So this is one of the mysteries of pattern formation or the emergence of patterns in turbulence. But one interesting way of trying to look at this problem, okay, is to take the Rayleigh-Bénard problem, take the model for this phenomena, right, which remember, still fluid, just at the onset of convection, flow is laminar. So you take the model for the laminar flow phenomena, and you say, I'm going to use this as a model for what is happening here at large scales. So what am I missing then? I'm missing, of course, the turbulence at the small scales. But I can now bring that in as a model using the Kryknen flow. So one way to understand this is to say, I take my laminar, right, pattern forming model for the large scales, and then to that I add, okay, the Kryknen model for small scale turbulent mixing. Right, so that would be an idea. Because what's surprising is, okay, I have turbulence here, there is some mechanism is giving rise to these ordered convection cells which are marked by the presence of clouds. Right? You can sort of understand, if I have these convection rolls where the fluid rises up, it will carry warm water vapor up and then it will condense. Right? So wherever it's going up, here there would be clouds, 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 clouds with some gap. So the presence of patterns in the clouds is a marker for the presence of organized convection cells, which you cannot see visibly. So the question really is, how does this pattern emerge and survive even though there is small-scale turbulent mixing happening? Okay. Of course, there is no real separation. As you know, turbulence has a spectra. So if I were to look at the energy spectra here, there would be turbulence across all the scales, right, in a power law. But again, to make some progress, we can artificially separate it out into large and small, and say the large scales I'm going to model with my usual Rayleigh-Bénard type physics. Right? And then I will add in these small scale mixing effects of the turbulence which I am not taking into account with a random field. Right? And if you, again, as a first approximation, say it's homogeneous and isotropic small scale behavior, you put in the Kryknen model. And of course, you can adjust this idea in different ways, accounting for non-isotropy of small scales and so on. But again, at leading order, this would be a good way to investigate the basic idea. Okay, and yes?
Does the same thing happen in the condensation following aircraft?
Yeah, I mean, sure. Whenever you see that, it's because water vapor or something is condensing.
So it's the same thing.
Same thing in what sense? No, no, it's not the same. I mean, it's not at all the same thing. No, there you have an aircraft going. That's why you have a line. So in the contrail of an aircraft, the contrail is straight because the aircraft is flying straight. No, so there is no mystery. Right? Here the mystery is nobody is flying straight. Right? Why am I getting ordered patterns of clouds when water vapor is everywhere? It should just be, if I had cloud patches forming randomly, then that's what I would expect. It's not like below the clouds I have some ship going or something. Right? That is different. Then you have a reason why you have some pattern, because something is making the pattern. What's interesting is nobody is coming and setting this up. It's happening spontaneously. Okay, so that's a pattern forming problem. You also have clouds forming and lightning occurring and whatnot in straight lines over shipping trails. But then there's a ship that's causing it somehow. It's still an interesting problem, but it's different. Right? Here the point is that how are you getting an organized pattern automatically when the turbulence is mixing things up? It should have completely destroyed the pattern. Right? So even though now I'm not, this is a big approximation, of course, I'm not accounting for how the small scale turbulence is coming, how it is being affected by the large scale pattern, all that is true. But even here it's interesting because it's saying I have some large scale mechanism to produce ordered patterns, and now I'm going to take small stirrers and stir everything up. Will the pattern survive or not? Right? Even this question, right, is not obvious, right? Because a stirrer may just stir up all these patterns here and destroy them. Okay, so we now have the machinery, in fact, to look at that problem, right? Because you can take the equations for this large-scale system. Wherever the velocity field is there, you can add a second, so you can take the velocity field of the large-scale laminar flow plus V turbulent, Vt, where Vt is directly put in from the Crichton model, which we saw in the last class. And then you study the phenomena only at the large scales. That means you look at the mean behavior or maybe its variance, right? And what have we learned from the last class? We've seen that if you look at the average behavior of such a model, the average of the laminar part will stay the same because the laminar part doesn't have any fluctuations, right? What will be averaging out is the fluctuations coming from the Crichton model. And you know that that part can be shown to just give rise to a diffusion. So indeed, one can show, using the result of the last class, that such a model will give you the behavior of the original laminar system with extra diffusion. Right? So this means qualitatively the system will do exactly what happened here, except it's somehow more stable. So if you needed a certain temperature to drive convection in this laminar problem, in the other problem the temperature would have to be higher because it's as if you have more viscosity, more thermal diffusivity, where the extra diffusion is coming from the Crichton model. And again, this diffusion will be orders of magnitude greater than the molecular diffusivity. Okay, so what it tells me, the simple model, is if I see rolls here at some temperature difference, which is non-dimensionally called the Rayleigh number, I would also see rolls in this model, but at a much larger Rayleigh number because of the presence of the Crichton field, because that gives a huge addition to the diffusivity of thermal, of energy, of mass, etc. And of course, diffusion tries to stabilize patterns. It will diffuse away, right? If there's diffusion, the effect of diffusivity would be to make everything homogeneous. So adding the Crichton model or accounting for small-scale stirring does try to destroy the patterns, right? Because it's adding to the diffusion. But it can be overcome if your pattern-forming mechanism is strong enough. Right? So in this simple model, it tells you is you will get the same phenomena, but at much, much larger temperature differences or much, much larger system sizes. Right? So Rayleigh number is proportional to the temperature difference into the height of the system to the cube and etc. And that's exactly what you see here, right? You get these patterns, but of course on a much bigger system, much bigger temperature difference. So at least at leading order, the results are interesting. Then of course one can do more detailed studies to probe this. So this has in fact already been done, right? It's from where I got this discussion, and that is in the following paper. I'll put it here. This was a very interesting paper that appeared recently in PRL, a few years ago. By Mikhail Wilczek and co-workers in Physical Review Letters. Okay, so they do exactly this. They take not the full equations for the Rayleigh-Bénard problem, but a kind of simplified model of this laminar pattern forming problem called the Swift-Hohenberg equation, which models this convection phenomena in the laminar system. Okay. To that model, they add in the Crichton mixing, and they are able to show what I said, right, that the Crichton flow gives rise to this diffusion, extra diffusion, which acts as an extra stabilization, but which can be overcome if you increase the Rayleigh number sufficiently, right? So that could be the height of the system for a given temperature difference. What it also does is it shifts the pattern to larger wavelengths. That means in the laminar model, if you have rolls of a certain size, with the extra diffusion, when you eventually become unstable, the rolls will be thicker. Right? So that would say, okay, compared to the analogous laminar system, this one which has that turbulent mixing will have larger scales, okay, which also makes sense. Because you have to be at very, very large scales for the small scale mixing to be like diffusion. And also, if you think about the laminar system, if I replace the fluid with another fluid with greater viscosity, right, and somehow manipulate the thermal properties so that the conductivity is also higher, I would get broader rolls coming in at larger system sizes. Okay, so all these things make sense. And there's some discussion in this paper about how these predictions compare with results from super large scale DNS. Okay, so one can see I just given you some examples here, okay, that there are several ways in which you can utilize what we've studied in the course to investigate how turbulence affects transport in different systems by replacing the turbulence with a random field, either the velocity field itself, as in the last class and this cloud state example, or some property of the velocity field. For example, here it would be the velocity gradient. Then there's another problem I've been mentioning again and again, where if you have turbulent flow going over a water surface and producing waves, right? Then the waves are forming because of the drag of the turbulent air. And you can just take the mean drag, in which case you'll still get waves. Because if you just take a free surface and you put a constant drag, you will get waves coming in as a kind of instability. But if you want to see what is the effect of the turbulence or the fluctuating drag, you can take drag plus fluctuation. But now you have to have some model for the fluctuation. That depends on how you decide to model the turbulence in the flow. Ideally speaking, it's flow near a boundary. So you should have the boundary layer, a turbulent boundary layer model. But again, you can maybe just add in white noise of some form as a first approximation, take it from there. But in this way, you can think of many examples where you can account for the effect of turbulence by replacing it with noise. Now, ideally, I would like to work out all of these problems, but that would be a different course. Okay? So if there's enough interest in person and online, maybe we can look at a course which does applications of these ideas. Okay? But the goal of this course was to give you the foundation. With this, hopefully, you can look at these papers and other papers, and you have the basic background to follow that literature. So with this, I thank you for your attention during this course. And let's see if we can come back to look at all of these things in detail. Okay, thank you.